crushed by air. Sounds pretty dramatic, right? But we're talking about something you've probably seen 100 times and never given a second thought: a massive steel storage tank. And yet, behind that simple metal shell, there's a constant battle raging against invisible forces, forces powerful enough to literally tear it apart.
I mean, it sounds impossible, doesn't it? These things are engineered to be incredibly strong, holding thousands of tons of liquid. But they can be crushed, literally flattened like an empty soda can. And not by some huge earthquake or a massive explosion, but by something as simple as a sudden change in the weather. So how on earth does that happen? Well, let's dive in and find out.
Okay, so it all comes down to this: a constant, two-sided threat. It's something that every single one of these large storage tanks has to deal with every minute of every single day.
So on one hand, you've got overpressure. That's pretty easy to imagine, right? Too much pressure builds up inside the tank, pushing outwards, and boom! It could rupture the seams or even explode. But then there's the other side of the coin, and this is the one that really surprises people: vacuum. This is when the pressure outside the tank is way greater than the pressure inside. And that creates this immense, invisible crushing force that can cause a total catastrophic implosion. Both of these are silent, invisible killers for a tank.
So, you might be wondering, how do engineers actually protect against these dangers? Well, they definitely don't guess. They follow a very specific set of instructions, basically a global safety rulebook that was designed for one reason: to stop these exact kinds of disasters from ever happening.
And that rulebook has a name: ISO 28300. It's the international standard for venting atmospheric and low-pressure storage tanks. It details exactly how you need to design the venting systems that let these tanks handle those intense pressure changes safely. You can really think of it as the definitive guide, the Bible even, for keeping these industrial giants standing.
And look, this isn't just some dusty old book of theory. No way. This standard is a living document. It's built from decades of real-world experience, from successes, for sure, but maybe more importantly from failures. It's the collected wisdom of countless engineers, all working to make sure the accidents of the past don't get repeated.
So to really get how this all works, we've got to think of the tank almost like a living thing. Yeah, really. We need to understand how it breathes. And that's actually what the standard calls it, more or less: normal venting.
So normal venting is all about the everyday stuff, the predictable pressure changes that happen because of daily operations or just changes in the weather. It's what the tank has to manage constantly just to stay balanced with the world around it.
The first big cause is something called thermal breathing. Imagine the sun just beating down on the tank all day. The air and the vapors from whatever's inside, they get hot and they expand. Just like when you exhale, the tank has to let that pressure out. It literally exhales all that expanding vapor through a special vent.
But here's where it gets really dangerous: the in-breath. Let's say you've got that hot day, and then bam, a sudden cool rainstorm rolls in. All those hot vapors inside the tank, they cool down and contract fast. This creates a crazy powerful vacuum. And to keep from being crushed, the tank has to immediately inhale air from the outside to balance the pressure. So yeah, a simple rain shower can literally be an existential threat to a massive steel tank.
And the second cause? It's even simpler. It's just moving stuff around. When you pump liquid into the tank, you're pushing out vapor. That vapor has to go somewhere, so it gets pushed out through the vent. And when you pump liquid out of the tank, you're leaving behind an empty space, a vacuum. And so air has to get pulled in to fill that void. It's super simple physics, but if you don't manage it right, the consequences can be huge.
Okay, so that's the day-to-day stuff. But what happens when things go way beyond normal? What about the absolute worst-case scenarios? Well, that's where the safety standard moves from just normal breathing to preparing the tank for what is basically a desperate gasp for survival.
And this has a name too: emergency venting. We're not talking about daily weather changes anymore. This is all about surviving an extreme, high-pressure event. And the most common and by far the most dangerous one is an external fire. Just think about it. If a fire breaks out right next to a tank, the intense heat starts to boil whatever liquid is inside. Now, this isn't just gentle expansion like from the sun. Oh no. This is rapid, violent vaporization. It creates a massive volume of high-pressure gas that will, without a doubt, turn that tank into a bomb if it can't be released, and released immediately.
The engineering challenge here is just immense.
And the standard gives engineers the precise calculations to solve it. This simplified table gives you an idea of how it works. It shows that the amount of venting you need is directly tied to what's called the wetted area. And that's basically the part of the tank surface that's getting hit by the fire and has liquid on the other side ready to boil. And as you can see, as that area gets bigger, the amount of venting required just absolutely skyrockets.
All right, so we've got the rules, we've got the math. Now let's check out the actual hardware, the physical tools engineers use to make all this protection happen.
Meet the workhorse of the system, the pressure/vacuum valve, or PV valve for short. This is pretty much the tank's primary set of lungs. It's a really clever, purely mechanical device that automatically opens up to let pressure out when things get too high, and then it opens the other way to let air in when a vacuum starts to form. Super important piece of kit.
But for a huge fire, a standard PV valve might just not be enough to handle the pressure. And that's why the standard has backups, other emergency measures. Some are pretty simple, like manhole covers that are literally designed to pop open under extreme pressure. But then there's something that is just incredibly clever, the frangible roof. Get this, it's a roof that's designed to fail safely. It's engineered to tear away from the tank shell if there's a catastrophic overpressure event. All that energy gets released straight up, but the main walls of the tank stay intact. It's exactly like a car's crumple zone, but for a gigantic industrial tank. Genius.
So I know that might seem like a whole lot of technical detail, but all of this invisible engineering, it has a very, very real and super important impact on all of our lives. And just think about this for a second. For a standard like ISO 2830 to even get published, it needs a yes vote from at least 75% of the international member organizations to weigh in. 75%. That represents a massive global consensus on what safety means, all built by experts from all over the planet.
Because at the end of the day, this isn't just about protecting a big metal can. It's a critical safety system. Following these rules is what stops a single accident from turning into a chain reaction disaster. It's what protects the lives of workers, the safety of the communities that live nearby, and, of course, the health of our environment.
So all of this incredible engineering is focused on solving the problems that we know about right now. But that really leaves us with one final big question to think about. As our industrial world keeps changing, as we develop new fuels, new chemicals, new ways of doing things, what new invisible forces are out there waiting for the next generation of engineers to find and to protect us from?